thinking a lot about ethics and statistics, and so I would. Does someone know how to make this like full screen, or is this what it's going to look like? Someone knows, right? Yeah, I've been thinking a lot about ethics and statistics, and then someone asked me to write something about whatever I want. So I thought, so I'm going to write like a little column in Chance magazine, which comes out every 3 months. So then I thought maybe after a few years of it, my thoughts will be more collected. But I thought I'd start that column by telling some stories, because I think that ethics is not really. I don't like how statisticians write about ethics and statistics. I think they focus on certain simplifications and try to overly mathematize the problem. Anyway, but that's not my topic today. I was just going to talk about it before we started. So since it's time to start, I'll talk about this instead. I was trying to figure out what to speak on here, and people had different thoughts. But my colleagues at Columbia who do computer science and machine learning told me that probably the people here don't have too much of a clue about Bayesian statistics, and maybe it would be good for me to demonstrate an example. Like instead of, I could have given a more technical talk about weakly informative priors and discuss ideas of regularization and what you get from putting in a little bit of prior information to structure your problem, and some discussion about how what's considered a statistical model is somewhat of a convention, that if you say, I'm going to fit a model using maximum likelihood or whatever, I'm going to choose the best fit in this space of all possible models, how is that space defined? It's somewhat conventional. So we say all Gaussian distributions are a two-dimensional space. But why is it defined that way? Like it includes things that are really sharp, like and really peaked, and things that are really, really, really broad. Well, they're different. They're much different. Why are they considered some part of the same family? Well, with Gaussians, maybe it's not such a big deal. But when you think about things like mixture models, and you realize that when people want to fit a mixture model, a continuous mixture model, they're often thinking about little multi-hump things like this. They're not really thinking about something where you have one spike that's really high and then a very broad distribution. That's not what they're talking about. They just happen to be in the same mathematical class. So sometimes when we put in a prior distribution, it's a matter of structuring what we're looking for. It could represent prior information that certain things are out there, but it could just be a description of what we want to fit. Just like if I decide to fit a normal distribution versus a gamma distribution, I can make that choice with no prior information. It's a choice. I'm deciding to fit a model with this distribution, or I'm deciding to fit a model with that distribution. It's a decision that I can make for many reasons. Similarly, the choice of prior can be viewed in the same way. I'm deciding to fit mixtures that look sort of humpy, not mixtures with a big spike, so I control the variance ratio. That's completely fine. That's one way we think about regularization. But I decided not to talk about that because my colleague said that a lot of you guys wouldn't really follow what I'm talking about because you don't really have experience doing that. So he said what I should really do is give an example of something where, hey, okay, so one thing is, so they said I should just give an example where Bayesian inference makes a difference and where you can really see where it does. And I said, well, I have a great example. It's 15-year-old research. Well, it's probably closer to 20-year-old research, but it was published 15 years ago. But he said, that's okay. It's like when you tell an old joke, it's only old if you've heard it before. It's really still a good example. In fact, maybe it's better, because then in the questions, people can ask questions like, if this is so great, how come no one's done it for the last 15 years? And then, he said that would be good, too. So I thought I would talk about this instead. Actually, I recently spoke on this at a conference on climate reconstruction, but that's okay, because this example has nothing to do with climate reconstruction anyway. So you'll be fine with that. Before beginning, I should say it's a pleasure. I've never spoken at this campus of Johns Hopkins University. I have fond memories of this area. I grew up in Maryland, in the suburbs of D.C., and we used to go up every year to Memorial Stadium. And I remember seeing Jim Palmer pitch a four-hitter and lose 1-0 once, and saw Brooks Robinson strike out a lot lots of things like that. So it is sort of fun to be here and give a talk. Feel free to interrupt at any point. The talk should go about 40 minutes, but you can interrupt. You don't need to save your questions to the end. Okay, so the story here is, actually, wait, I'm going to get my clicker here so that I can point. I forgot to set that up. I think I have it in here somewhere. My story is about dry cleaning fluid, which can be bad for you if you breathe in. If you continue, why is it doing this stuff? Can someone help here? Computer scientist, help get this working. Okay. Okay. Doesn't work. Okay, well, I'll use this stupid thing then. Okay. Okay, so the story is that dry cleaning fluid can give you cancer, and so you don't want to be exposed to a lot of it. But in this case, we're interested in studying what extremely low doses do to you. Extremely low doses aren't so bad, but there's actually a lot of chemicals that are bad for you, and you're getting a lot of them. Each one might not be so bad in an extremely low dose, but together maybe it's not such a good thing. The punchline is that we use Bayesian inference, and we are able to fit a model that we otherwise couldn't fit. And it's like a Rubik's Cube. All the different pieces fit together, and that's what I'm trying to convey here. And then we can discuss it. So some of the background, as I said, is I wrote high doses. We want to actually estimate how much PERC is metabolized at low doses also. The crude story of the biology is that you breathe it in, it goes through your blood, and some of it goes into your liver, and in your liver some of it is metabolized, and the metabolites can cause you cancer. So you just don't want it in your liver. There was an experiment done where 6 healthy volunteers were exposed to the stuff, and then they measured the concentration in their blood and exhaled air right away, then after 15 minutes and after an hour, and a few more times over the next 2-week period. This is what's called a stiff system. It's has changes on many different time scales. So at a short time scale, once you leave the room that's full of PERC, the concentration in your body starts dropping really fast because you're breathing the stuff out. But in the meantime, some of it's been stored in your fatty tissues, and it can be stored there for a really long time. Just like, if you ever go to a club and then you come home in the evening, you might pull out your handkerchief and blow your nose, and it smells like smoke. Or your hair might smell like smoke, which is sort of funny because maybe the club didn't smell that smoky, but your handkerchief can hold a very high concentration of smoke in it for a long time. Similarly, your fatty tissues can hold a high concentration. Now, this is important for computer science purposes because in modeling this system, you need to model things at a very short time scale for a long time, which means it takes a long time to actually compute the system because you basically have to run a differential equation solver over a 1-minute time scale, but run it for 2 weeks. I guess I have to keep touching this to get to work. They should devise a computer program that would just, like a little, maybe you all could make like a little robot which every 2 seconds would touch the thing so that it wouldn't go back. Like a mechanical device maybe, a sort of like, steampunk or whatever, would just like touch it and then come back up. And yeah, but you'd have to wind it. Yeah, it would be, you could plug it into the USB so it would keep the power because there's no perpetual motion machine. Maybe one of you teams could do that. So we fit a 4-compartment model, which I'll talk about. And the story is that you couldn't just fit the data. We needed Bayesian inference. I think I'll say that a few more times to make the point. Here it is. Good old 1993 graphics technology for you. You breathe the stuff in, Some of it you breathe out. The lines are blood, and some of the blood goes through your well-perfused tissues, some through your poorly perfused tissues, some through your fat, and some through your liver. In your liver, it gets metabolized. These are all linear differential equations saying that if there's more in the blood and less in here, then it will flow into here. And then there are some nonlinear differential equations approximating how it gets metabolized in the liver. This is all very standard. The model has a lot of parameters. There's the percentage of blood flow through every part of the body. There's the volume of each part of the body. There's the equilibrium concentration of perk in the different parts. There's how you breathe, a couple of these things too. This is, of course, a simplified model, which you could say in two ways. Either it's simplified because there are only 4 compartments, and personally I have more than 4 compartments myself in me. Or you could say it's simplified because if I really want to consider myself as 4 compartments, my compartments are not completely homogeneous. And indeed, this model is not correct because it assumes instantaneous equilibrium within any compartment. We're not so worried about that because if we're looking at exposure of low doses over a long time, you'll probably be sort of in equilibrium. But it's just good to recognize that. What the data look like. We have data on 6 subjects. I'm showing you only 2 of them, so it's clearer. You can pick out the people. Each person was given 2 exposures. First, he was exposed at 72 parts per million for 4 hours, and then followed up over 2 weeks. And second, he was exposed again at a higher dose and followed up over 2 weeks. Then you see the concentration in exhaled air and in blood for each person. There might be better ways of graphing this. For example, you might consider graphing exhaled air versus blood or whatever. You might consider it's declining like this exponentially, so maybe we should have plotted on the log scale, right? But it is on the log scale. It's declining on the log. It's sort of funny. So if there was only 1 compartment, it would just decline linearly on the log scale because it would just seeps out of you. Actually, what's happening is first it's declining, going out of your blood, then it's going out of your well-perfused tissues, it's going out of your poorly perfused tissues in your liver, and finally it's still leaving your fat. So every kink in this curve, roughly speaking, represents a compartment. And somehow in the old days, maybe even today in the new days, people decide what model to fit based on how many kinks there are. And you'd feel sort of bad fitting a 1 compartment or even a 2 compartment model to data such as this. Can you all hear me in the back? Okay. Oh, also, our model has about 18 parameters for each person. It's hard to believe. Well, I guess we probably have about 18 data points for each person, so it looks like we can fit it perfectly. But, yeah, the model isn't perfect. We can't really do that. So what can't we do? So we can't just fit a 4-compartment model. Just what happens when you fit the 4-compartment model. If you actually just fit it directly, you can fit the data and you get unphysical parameters, like people with 8-pound livers. Whatever it takes to fit the data is more whatever it takes than I'm willing to take. The next idea was, I called it assisted model fit, that they would take the model and they would take a few parameters. Wait, do I have a slide for each? I do. I better talk them through in order. So here are some ideas that didn't work. I said fit the model directly to data, assisted model fit a simpler model, or just use the prior. And I'll do each one. So fitting the model directly to data, it's what physicist types call nonlinear least squares. And I said when you do this, it's just not going to work. It's unstable. Well, I had 6 subjects, so I could really have 180 data points by pooling. But the thing is, I could estimate the exposure, the response in the standard man, but I'm not really interested in the standard man because we're interested in the population variation. Some people are more susceptible to a toxin than others, and we want to estimate that. That was a key part of the study. We could not simply pool the data together. That was disallowed by our goals, our research goals. Now, in assisted model fit, you say, well, there are some parameters we sort of know. Like I just told you I knew how big people's livers are pretty much. And you have an idea of how heavy different people's... And fatty tissue, you can estimate that by putting people in a bathtub. And they actually do certain things like that. So you should be able to put a few parameters in. So you don't have 15 parameters to estimate for each person. You might have only a few. The hard part, though, is the few that you have remaining are the hard ones to estimate. And so actually it doesn't quite work in two ways. One is you don't know these top parameters that well. And it turns out when you try to put numbers in for them and you try to fit the rest of the data, you can't always fit the data well. Then the other problem is that these key parameters, they're key parameters you know almost nothing about. Like what's the equilibrium concentration of PERK in the fatty tissue compared to the blood? I don't know that. That's why I did this study, right? A simpler model, this is what people often do, fit a one-compartment model or a two-compartment model. That's easy, but it doesn't fit the data. It's hard to get this stiff system replicated. And it's too bad it doesn't fit the data. Not everything fits the data. Why should I care? I care because our goal is low-dose extrapolation. So low doses, well, the funny thing is we have data at low doses. Because look, we have data at high doses because people are given high doses here. I'm just telling you those are high doses. But then down here, people have low doses. So we have low dose data. But to estimate low dose, if we fit a two-compartment model from the data and most of the data are up there, then we're going to be estimating the high dose behavior and not extrapolating the way we want. Now you could imagine a way of solving that. Like you could say, I'm going to fit the data, but I'm going to actually do nonlinear least squares, but I want to fit these data better because I have fewer data points here. So maybe I'll do a weighting function. So I'll say that instead of doing maximum likelihood, I'll do maximum weighted likelihood, and I'll weight these points more, and then I'm fitting the low dose behavior better. Maybe you could do that. It's sort of a research project in its own, and it takes you a little bit away from the science of the problem. So we didn't have any great interest in sort of knocking ourselves out, coming up with a clever statistical solution that didn't use additional scientific information. The last thing that didn't work was simulating from the prior. So my colleague did a literature review and got priors for all 18 parameters. Even the things that you don't know anything about, like the equilibrium concentration for PERK, well, you might know about the equilibrium concentration of some other chemicals, so you can get some vague idea, for example, that the fatty tissue holds more than the blood of a lot of different things. So they got a fairly vague prior distribution, and then they just started drawing samples from the prior, thinking that if you draw enough samples from the prior, eventually you'll get lucky and you'll find a vector of parameters that fit the data, and then you're happy. Well, that's actually a very crude way of doing Bayesian inference. And more recently, it's related to this idea called approximate Bayesian computation. So it's not necessarily a bad idea, but there's a reason why it's a big computing topic now, because you can't do it just by drawing from the prior. It's more complicated than that. Simply drawing from the prior, you get draw after draw after draw that looks reasonable but doesn't fit the data over and over and over again. And as I said, it's hard to get good prior information for some of these parameters. So what did we do? We did Bayesian inference. So it was a funny case, actually unusual in that a lot of the Bayesian inference problems I've been involved in use very little prior information. And in my books, I tend to downplay prior information and mostly focus on problems where I can use the structure of the model to estimate hyperparameters. This is an interesting example because we needed real prior information for it to work. That's the only way it could have happened. And in fact, this guy came to me because he wanted to combine data and prior information. And he called somebody up and he said, well, there's somebody in town who combines data and prior information. So he came by my office and we started working together. So we have our model, we have our parameters, and we have to specify our prior information. We have, I mentioned the data already. So some parameters you know a lot about, and some other parameters you don't know so much. Michaelis-Menten coefficient is one of the parameters governing the rate of metabolism of the toxin. It's very important. A key part of our model is that it includes uncertainty and variation parameterized separately. And I'd better check to see if I have a slide on that. I do, so I'll get to that. This is super important. Then we did posterior simulation, which we used a Metropolis algorithm. Actually, as a byproduct of this project, we did a little research project to estimate what was the most efficient high-dimensional Metropolis jumping rule. And we found out that these rules are most efficient when you accepted about 1/4 of the jumps, which we then implemented in this project. And then since then, other people have used this rule. But like many theoretical ideas, it was actually motivated by an applied problem. So we wrote a program which, it actually still exists. It's that computes these models in general. I don't know how many examples it's being used for, but it's out there. The key part that made the program really work was the function that evaluated the likelihood, which ran a differential equation solver so the way the program actually works is that you have a guess of the parameters. You then take the guess of the parameters and you use that to create a curve of expected data if the model were true, and then you compute the likelihood, which is just the sum of the squared errors off the curve, and then you go from there. So it's not magic. You still need a differential equation solver inside to get it all to work. Yes?
Right. Is that the notion that you have Gaussian noise added to the differential equations? Is there a scientific reason to believe that's right?
There's no particular. So yeah, the noise model seemed to fit the data reasonably. Yeah, measurement error model. Right. So there was no particular scientific justification for that model, which lumps together model error, measurement error, and various, I guess, sort of systematic lab errors. We did test, and we found no evidence of correlation, time correlation between the errors. So, which we took that to mean that the 4-compartment model fit reasonably well. But yeah, we didn't really think too hard about the error. Is the answer. And then once we fit the model, we created inference. And I'll just quickly say that in addition to learning about parameters in the model, you also want to learn about predictions and inferences of things that aren't parameters. So in particular, we estimated all these parameters for this 15 people. We also, since it's a hierarchical model, we estimated the distribution of these parameters, which means we estimated about people in general, actually, I guess, young men in general, since these were 6 young men in the study, but a population. But we actually didn't care directly about these parameters. So once we had the parameters for each of our posterior simulations, we piped through a new set of initial conditions. Our new set of initial conditions is what if you expose people for life or indefinitely at a low dose, how much gets metabolized. So that's, mathematically speaking, the outcome is a function of these 15 parameters, which we compute by running the model. I want to emphasize this because in a lot of model fitting, especially including Bayesian model fitting, people stop when they have the parameter estimate. So they think their goal is to estimate a parameter and get standard errors or whatever. In this case, no, the parameters are a means to an end. And then finally, we check the model. There's a saying, I believe it was, I'm not sure whether it's attributable to Thomas Bayes or Laplace, who's said to be the first applied Bayesian, with great power comes great responsibility. And when we fit a model, a Bayesian model, we have this great power. We can make posterior statements about everything, which is not true of classical statistics. Classical statistics is very limited in what it is willing to make statements about. But now that we have that power, we have the responsibility to check our model. And just as a chicken is sometimes said to be an egg's way of making another egg, similarly, all of Bayesian inference can be thought of as simply a way of checking a model. So Bayesian inference can make so many predictions. You have some data and a model, you make so many predictions. There's so many ways to check the model. There's so many ways to falsify yourself, which you could say is really your goal, is to find out what you're doing wrong. That's not always the case. In science, I think your goal is to find out what you're doing wrong. In engineering, in policy, your goal is to get a reasonable answer. So in some sense, as scientists, we actually want to know why the 4-compartment model isn't right and what's wrong with it. As public health officials, we're interested in getting our best estimate right now of the rate of metabolism at low dose. We're doing both at once. We want to eat the chicken and we want to make another egg, yes. Which I guess we can do as long as we make the egg first and then eat the whatever. Okay. Now what? Okay, I was like yammering on about the priors, so I want to talk about this. This is important. I would never display things in a table like this. This is the old me. I feel a little bad about it. But I mean, not so bad that I remade this. So I'll go through these, not because you care, or because even I care, but to give you a feel for what's happening. The ventilation over perfusion ratio, that has something to do with what goes in when you breathe it in, the air compared to the blood. Our prior distribution is it's a log normal distribution with a center of 1.6 and a geometric mean of 1.6 and geometric standard deviation of 1.3. That is, the log of it is a normal distribution with mean log 1.6 and standard deviation log 1.3. We have a truncation of 3 here, which means that everything's truncated at 3. This is a little trick we did. I really like this. I haven't used it since. We truncated all our priors at 3 standard deviations, 3 prior standard deviations. So when we actually ran the model, if we're ever outside of 3 prior standard deviations from the mean, we don't keep jumping out there. We just keep it there. So we reject those jumps. So then when you're running the model, sometimes you better turn off the speaker for the mic for a second because you don't want to hear it. But sometimes we make a mistake and do things wrong. Sorry, the people in the back didn't hear. So you can tell them what I said. And anyway, sometimes, yeah, we make a mistake. And actually, this was a cute little debugging trick, which, as I said, I've never done since, but it worked here, that sometimes you get your posterior inference for some parameters would be all bundled up at 3 standard deviations away because there was a mistake in the model and it was trying to pull things over. And it was just really easy to see that diagnostically. Now, there'd be other diagnostics. You could have an untruncated model and just compute the average number of standard deviations away something is. It's like there are a lot of things out there you can do. That was particularly what we did. We have parameters that sum to 1, and we actually did a little research project. We used softmax to parameterize these, but you need to set the parameters, and we came up with a clever way of doing that. I'll tell you the tough part, though, and was it in the next? No, I don't have it. I don't have all the numbers here. So I want to show you this parameter. So this parameter had a prior of 0.042 and a prior geometric mean of 0.042 and a prior geometric standard deviation of 10. So what that says is that I think that I don't really know where it is, right? Because I think it's probably somewhere between 0.00042 and 4.2. Like, it could just be anywhere. But that's like no information at all, but I really don't know much. So what do? So what we did, we set up a hierarchical prior. What we did is we said that I actually see this number 2 here. What we said was that there are 6 values of this parameter because each person has one. So I said the 6 values of this parameter come from a distribution which we estimate as having some mean with a standard deviation of 2. Actually, it wasn't 2. The number 2 was estimated from the data 2 with a strong prior. I won't get into that. So basically, we said all 6 people are either sort of right around here, or maybe they're right around here, or maybe they're right around here. So I said the center could be anywhere. The center is from a distribution with this, with a standard deviation of 10 on the log scale, or log 10 on the log scale. But all 6 of the people are probably close to each other. And that's, let me just finish my, okay, so that's a hierarchical prior, and it's completely mathematically kosher, but in the literature you don't usually see this. People say, what's your prior? Well, there are 6 parameters here. each person has them. So it's a hierarchical model. I'm saying that my prior knowledge about those 6 parameters is correlated. They're all here, or they're all here, or they're all here. They're all probably close to each other. This allows me to make use of the fact that I have many people's data without trying to specify it. So there's no reason you can't do it, but people don't usually think about it. Yes?
So this is what you meant by uncertainty versus variation?
Yes, that's what I meant by uncertainty versus variation. Uncertainty, the factor of 10 is the uncertainty. The factor of 2 is the variation. Yes?
Do you have a moment for a digression on your comment that
Yeah.
you don't see this much in the literature?
Yeah.
I think in the literature that I read, and many people here read, we see hierarchical models all the time for exactly this reason. So are you making a comment about 15 years ago or about the other parts of the statistics community that don't work on language and speech? Or?
I'm talking about everybody but you, basically. Actually, even all the other people in the room, I mean, really don't know what they're talking about. You're really the only one who... No. What I'm saying is, yeah, people use hierarchical models all the time. I mean, not enough maybe, and more than they did 15 years ago. But in this case, I'm particularly talking about an informative prior. So people tend to use hierarchical models for hierarchical data. Now, these are hierarchical data because it's multiple people. But people, like, if you're in a situation, it's like, I have these damn parameters and I need to put a prior on because I have information. People tend to say, what's your prior information? And try to specify it directly as a number, rather than to say, my prior information itself can be expressed in this hierarchical way. It might very well be people do this all the time in speech, and I'm just not aware of it. But yeah, that was the distinction that I was making was about actually putting in quantitative prior information in this way.
I mean, of course, there's a simpler thing that I think might be more widespread. A similar thing that I think might be more widespread outside the Bayesian framework, where somebody's doing something like logistic regression, and you throw in features that are shared across subjects, as well as features that are within subjects, and with a regularizer that has the same effect.
Yeah, there are many ways of implementing it, right? I mean, you can say, in a sense, like you say, well, there's a latent parameter here. So, sure, I set up the model so that there was a latent parameter, which was the population mean of these. So what I'm really doing is I'm putting one prior. Actually, what I'm actually doing is I'm putting this prior in the population mean, and then on the population SD, I'm putting a prior centered at log 2. So it's trivial in that way. I think that I don't usually see people doing this particular trick, but I'm happy if you tell me people do it all the time. I said this already. We fit the model. We use a Gibbs sampler and Metropolis algorithm. We took a random walk through the space. I think nowadays maybe I'd rather do it in Stan, but this was pretty good for 1995. Or I guess it was earlier when we actually did it, like 93 or 94. I took a lot of debugging, not just the obvious debugging, but like you fit the model and it gives a result that doesn't make sense and you have to think what's going on. At one point, we looked at the posterior correlations of the parameters, which isn't what you might think it is, because usually in the Bayesian world, when people say they look at the posterior correlation of a parameter, they're thinking that I have 2 parameters in the model and I have a bunch of simulations and I look at how they're correlated. But that's actually not what I'm talking about. What I'm saying is we looked at the estimated correlations of parameters across the 6 people in the experiment. We found certain things very highly correlated. Like, I can't remember. There were 2, like it was like the volume of the well-perfused tissue. And 2 of these things were very highly correlated. It didn't make sense to say, well, people with really big, well-perfused tissues should have really high this. Like, it made no sense. And it turned out that there was a problem in the specification of our model. So we fixed that. So we're fitting the model a lot. My point is, it's not like people have this thing like, oh, yeah, I do it. And then, like, I run the model for 2 weeks to get the answer. And there's some people in statistical computing, they're real tough guys. I would write a paper saying, well, we did 1,000 iterations of our model and it converged in 5 minutes. And the tough guy's like, oh, how do you know it really converged? I run my models overnight. I run it for 1 million iterations because I know how to program. Right? And it's like, well, I don't want to run it overnight maybe because maybe I want to try some different things. So that's why I like arguing with someone saying here, which is pretty lame, actually, get down to it. Okay, so we did a lot of checking and a lot of working things through. Then, as I said, once we liked the model, we reran it under different initial conditions to figure out what would happen under different things, which was the goal. Here's an example of our inferences. These are our 6 subjects. In the y-axis, we're plotting the percent metabolized at low exposure, and the x-axis, the percent metabolized at high exposure. It's a little weird if you start getting this. At high exposure, about 1% is metabolized, and at low exposure, about 40% is metabolized, which sort of seems weird because like high should be as low and low as high, but of course it's right, because at high exposure, it saturates. Your liver can just not process this stuff fast enough, and eventually it just goes out of your body. At low exposure, your body can process a lot of it. You might wonder why it's not 100%, because some of it never reaches your liver. It goes through your other tissues and flows out. That's why you need all those compartments. The fatty tissue is not really so important, because it's just sitting there absorbing the stuff. The fatty tissue is important to fit the data. It's a funny thing. We need to fit the data, but not really. Now it doesn't matter anymore. So you can see some estimated population variation. It looks like person E metabolizes a lot, and person D, there's more uncertainty. And each dot is a posterior simulation here. That's the kind of thing that you would do, to summarize. We can get population inference. We ran a lot of simulations, so we broke this into a grid. And for each grid, we ran the model on a bunch of people from randomly drawn from the estimated population. We actually, mathematically, we created person 7, who was a random draw, who was from the same population as persons 1 through 6 and had no data. It was easy to do. At low exposure, people metabolize a certain amount, and then at some point, the threshold kicks in, and this has a slope of -1, which means at this point, no matter how much you get, you're just metabolizing it at the maximum rate. And it's a curve rather than a solid line because there's uncertainty and because there's variation. So any given person, you don't know exactly where they're going to be. And these are uncertainty bounds. You can use the model to externally validate your model. Here is some new data. And then we ran on the same people with their physical parameters and their initial conditions. We ran the model a bunch of times and got, I don't know what if these are 90%, 95% bounds, something like that. Yes?
How much do your uncertainty bounds depend on your decision to truncate the priors?
Oh, the uncertainty bounds don't really depend at all on their decision to truncate the priors, because nothing is out at 3 prior standard deviations in this really. That was really just a debugging thing. There's no way it can really matter in this case. Because they're Gaussian priors. Like if you use priors like Cauchy type priors that could be really flat, then wherever you truncate, you could be sort of losing something.
But even here where you're like, so I assume that solid line is plus or minus 2 standard deviations. And if you're trunking the priors at 2 standard deviations, that would seem like...
Oh, no, well, we're truncating them at 3 standard deviations, but it was 3 prior standard deviations. This is posterior, so they're sort of inside the prior. Because although the prior was informative, was not as informative as the data. I mean, anyway, I can't. It would be worth looking at. I mean, that's another way of saying it. Is one could. I'll show you another graph which addresses this a little bit. It's not a stupid question at all. Yes.
Another related question: if you have the hyperparameter, the dispersion parameter that is going to be the estimation, and you're truncating based on that, what have you used to inform that hyperparameter or the hyperparameter?
Oh well. The thing that said that they were all within a factor of 2 of each other, that one I think we gave I think we actually gave them like inverse chi-squared priors centered at 2 with 2 degrees of freedom, so it could sort of be estimated. There's not a huge amount of data on that sort of thing, so you end up with a fair amount of posterior uncertainty also. It sort of anchors things. I mean, you definitely, if you really want to trust these predictions for new people in the population, you have to think what information you have. Let me draw an analogy. I've spent a lot of time, well, not a lot of time, I've spent some time making models for forecasting elections. Not so much because I care about forecasting elections. It happened because about 20 years ago, my colleague and I wrote a paper. We're working on a paper called why do presidential opinion polls, pre-election polls, vary so much when elections are so predictable? Polls jump all over the place, but yet people know ahead of time who's going to win the election. So to do that, we needed to fit a model to predict elections, really just to demonstrate that it could be done. I mean, people have done it before, but we wanted to do it ourselves. So we fit a hierarchical model because you're predicting the election outcome by state, and we have error terms at the state level and the regional level and the year level. So there's sort of residual error from any model at the year level. When you fit these models to the next election, they'll tend to do pretty well. But they give uncertainty bounds which seem too wide. And I think what happened is that we put flat priors on our variance parameters, and you don't have that many election years to fit. And with a flat prior in your variance parameter, you get these sort of a bit of a long tail from the likelihood. So you get a small but non-zero probability of extreme things happening that you don't really believe, because it has to do with the application of your model. That like what am I going to do with a 99.9% probability forecast for the election outcome? Like, so there's a 0.01% chance that all sorts of weird things are going to happen. So like that would be outside of your model in the first place. So getting to this, at some point there always is this tension. To what extent is this project a data summary, and to what extent is it our best inference for the population? Our goal is to be our best inference for the population, but it's clearly centered on this data set, and a lot of its value is that it's a data summary, right? When we prepare the report and it's read by policy people, it's relevant that this is a summary of this actual experiment in a way that, like, it's different than if my colleague just said, I'm an expert and my guess is that it gets metabolized at a 2% rate or whatever, right? So it's like, so here we have these priors and they guide us, but we recognize that these are somehow data-based inferences. I guess the idea is that, like, the concept of data-based inference isn't always so clear. Like, maximum likelihood is a pure data-based inference. Well, not really. It's data-based plus the fact that you decided to use maximum likelihood that day, right? So we're putting in priors, but we're still trying to be data-based. We have to say what we did. Let me continue. When's this thing? If someone could build that touching thing, that would be great. Okay, so here are some data. Now, the model doesn't quite fit the data, you see. Look at the x-axis, it's time. And remember, I said that our model assumes that the compartments are instantaneously mixing. And so in this particular experiment, it really was not quite working well because for the first few minutes, it didn't capture that. So that's okay. We're not so bothered by that. You know, I'm a big believer in graphical model checking. And you sometimes see this in statistics books more and more, because every time I come up with a new book, you'll see more of it. But you don't see so much in research articles. And I have a sociological story about this. And the sociological story is that when would you put a model check in? Well, if you put this in your article, like, then the reviewers are going to say your model doesn't fit, so you should fix it. And then once you fixed it, you don't need the graph to show that it fits. You can just say it fits. So, well, we got this graph into the article, but like it's sort of still there's something like that going on. Okay, so I said what we did. We fit the model with uncertainty and population variation. We fit it to data. We checked the inferences, and then we reran under these other conditions. And then I have the key. Okay. What have we done since 1995? So I have not really done much on toxicology since then. I've worked on some little projects. This slide would look better if it were 1995, because then I could say this is what we're planning to do. But there are a few things you want. You do want to obviously automate the inference. You don't want to have to write the big program each time. We'd like more models, bigger models. So 4 compartments is still sort of like, there's sort of two worlds out there. There's a world of people who feel uncomfortable with 4-compartment models because they feel they can't really fit them and they want 1- and 2-compartment models. And then there's a world of people who've been out there fitting 12-compartment models for a long time, and like, who knows what it all means. So we'd really like to do that. Then the big thing is there are thousands of toxins. So there are actually very few toxins where there have even been experiments like this. So if this whole procedure, including the experimentation, were wrapped in a box and somebody could do it, then maybe the government could, give out a grant and say, do the experiment, run it through, and do that for a lot of different toxins. It can't be if it's a big research project each time. So that's where we'd like to head. Wait a second, I should figure out where I am. Okay. I'm now getting into the, like, how does it all fit together part. And I have 5 pieces to it. And I'm going to talk about each of the 5 pieces. The first 2 pieces are things that come from, that are contributions. Okay, let me get to the 5. These are not the same 5 as I'm going to get to. But let me talk about this slide first. So first, I want to say, as a statistician, what I contributed to pharmacology, and the idea of using Bayesian inference, like, that's a biggie, right? Like, people really do want to combine different sources of information. Using hierarchical models, that's a statistical idea that got adapted here. What did the toxicology example give us as statisticians? Well, we created new models for constrained parameters. This idea of the hierarchical prior distributions I had never seen before, set up that way. We were forced to do it by the application. And also, a lot of these graphical ideas for model checking we developed because of this project. So, as is often the case in statistics, we're motivated to do good things because we need to. Statistics, I always say this, that any problem I work on, I try to do the dumbest possible thing to get out of that project. That's always true, right? Like, any project, you're all excited about starting it. The second you start, you want to get out of it. You want to end it. It's like, when's it? It would be as if you go to the movies and, it's like, okay, when can I go, right? So that's the way research is. You start it and you want to finish it immediately. But the unfortunate thing is that although I want to do the simplest possible thing, it turns out that in almost every research project, any project I've ever been involved in, the simplest possible thing that works is just a little beyond the most complicated thing I know how to do. So I have to do some research. Now I remember, I have 7 things, and we need all 7. And that's what I'm going to finish my talk with. The physiological model, when I say physiological, I mean it's a model that's sort of like a human body, rather than a phenomenological model like y equals ae to the minus bx plus ce to the minus dx, whatever. It's a picture of the body. A hierarchical model. Actual prior information, not a flat prior or non-informative prior, real prior. Data, actual experiment. Bayesian inference. Big computing won't seem big to you. Everything I do is trivial compared to everything you do in computing. And model checking. All 7. Any 6 of these alone, it wouldn't work. Why did we need the physiological model? Well, we couldn't, without a real physiological model in which the parameters meant something, we couldn't get prior information, right? You can't get prior information on, if I said the model is ae to the minus bx plus ce to the minus dx plus ee to the minus fx, I'd say, what's my prior information on d? What is that, right? Okay, but I can say what's the prior information on the volume of the liver, because that's a physical thing. Okay. And that's one part. The second part is because we want to extrapolate to the general population. And these are the things that we think people are similar on, are these physiological parameters. That's what we want. And it's also true for allometric scaling. So if I want allometric scaling is you have estimates from animals and then you scale them to people, it's much more reasonable to scale these little pieces from the animals, like the relative volumes of different compartments, than it would be to scale like curvatures of functions that don't have any meaning. So this is key, the physiological model. If we just did data fitting, first, we can't just do data fitting. Second, if we just did data fitting, then the extrapolation to the population would be suspect and hard to validate in any way. Yeah, do you have a question or just this?
Well, I'm hesitating about whether to interrupt at this point. Maybe we'll go through.
You can interrupt.
Okay, so I just want to push back a little bit on the notion that there's no good way to get prior information on the parameters. I mean, I kind of struggle with this issue. So I mentioned logistic regression before. So people often regularize that for good reason. And I usually think of the regularizer as being a log prior term. So, there's some prior information about what the parameters of the true classifier or true conditional distribution are. And then I say, wait a minute, what's really going on is not, the data is not really being generated through this model. In fact, the true conditional distribution comes from a physiological model or something, and then you conditionalize it. And so I don't believe that there are true parameters of this thing. Nonetheless, I might be able to say,
no, I see where you're coming from.
A really bad model of the conditional distribution, and I know something about what it
wait,
to be thanks to other species.
Right. Okay, so, I mean, yeah, you would have liked my other talk that I didn't give, but I would, sure, I mean, you could say that every parameter, no matter how meaningless, has a prior which corresponds to the set of values of that parameter that you might see when the model gets into your computer. I mean, there's a sort of empirical prior for everything, but it would be hard to estimate that from the literature. So you could actually go to the literature and try to see how big people's livers are. But it would be hard to go to the literature and see how big beta 3 is. Even though, so to get the prior for beta 3, you'd presumably have to do an analysis such as this to map it to the literature. So it wouldn't just come out.
Right, but if you had, for example, curves, similar curves for rats and
right.
species and so on.
Oh yeah, no. If
you might be able to get a notion of what the curve fitting parameters look like.
Oh sure. If I had lots of data like this, yeah. But the point is, I might not have I might know how big a rat liver is or a human liver without having curves like this. There are a lot of ways of estimating how big someone's liver is or even equilibrium concentrations other than sticking them in a room for 4 hours with perk and waiting for 2 weeks. So yeah, that's the whole, I mean, this is another way of putting it, is that like some old-time positivists are like, there's no parameters, there's only predictions. But parameters are those things that sort of apply to a lot of predictions, right? So the physiological parameters can sort of come up all over the place in a way that the phenomenological parameters might not. The hierarchical model, two things. I said we need the hierarchical model because we don't have enough data from each person. And so indeed, if I had a lot of data from each person, I could really estimate from each person, and then I don't need a hierarchical model, right? Because if I told you I had 6 people, and I have a good estimate for each person on how much he metabolizes, then I could give those 6 numbers to the regulators, and they can draw a distribution through 6 points almost as well as I can, right? A hierarchical model is needed because I don't have enough data on each person. I have to do partial pooling. But I can't do complete pooling because I'm interested in the variation. Okay, we need prior information and experimental data. Those are the 2 pieces of information. The experimental data are, I would say they're more important in the context of a statistical analysis. On the other hand, given that we have thousands of toxins without the experimental data, there's sort of other categories of data too. So I have prior information, experimental data, then there's observational data. Like prior information sort of means whatever's not in your data set that you still want to include, right? So there's a lot of other things that could be used here. This is a fairly clean study because we have a clean experiment. It could be made more difficult if our data were more diffuse. And again, another way of putting it is that prior information is another way of saying crappy data analysis, right? So instead of really analyzing all the old data, my colleague reads through the literature and comes up with a prior. That's obviously not the optimal method of data analysis, but it's better than doing nothing. And we need them both. Neither one alone would work. We need Bayesian inference, as I said. or something like Bayesian inference. Like, you don't ever, we always say this in statistics, like, you have some movie and you want it to open big. You want to sell lots of tickets, and you want it to be a good movie. Okay, it's going to be an action movie. You want the actor to be charming. Okay, you don't need Tom Cruise. Okay, all you need is someone who has all the properties of Tom Cruise. You don't need Tom Cruise himself, just someone who's very good looking. Height doesn't matter maybe so much. Is well known, charming, and can act pretty well, so forth. Similarly, we don't need Bayesian inference. All we need is a method of inference that does what Bayesian inference does. Okay, so I can do anything a Bayesian can do, a classical researcher can do. All you have to do is the simplest way would be to hire a Bayesian, get him to analyze the data, find out, take his computer program, call it an estimator, and then just to be safe, kill the Bayesian so there's no evidence. And then it's an estimator. And then you can maybe hire a theoretical statistician to evaluate its statistical properties, and you're done, as long as you don't have a lot of scruples. Of course, a classical statistician with a lot of scruples wouldn't like that procedure because it regularizes things. But you could maybe give that a different name, and that would be fine. So I have no big. I'm not trying to sell you Bayesianism. I'm just trying to tell you what works. We did not have another approach that was able to combine the prior information and the data in this way. Of course, there are other problems where there are very natural solutions which do not derive from Bayesian principles. I'm not trying to say that every problem is most effectively attacked in a Bayesian way. I'm merely saying that you can give anything any name. And a Bayesian approach is particularly pleasant for problems with uncertainty and variability because that's what Bayes is good at. Maybe there are other sorts of problems where Bayes is not so good at because it spends so much of its computational effort dealing with uncertainty and variability. And there are problems where you have to analyze huge streams of data, and there are certain problems where if you do a Bayesian analysis, you just can't analyze the data as fast. And getting a great estimate of your uncertainty is not as good as getting more data and just getting the damn answer. Right? But in this case, we have a limited amount of data, so it seemed appropriate. We needed to compute. We needed to write a computer program. You couldn't just, their existing things weren't possible. So a key part of everything we did that made it work was our inclination and ability to compute. This was 1995. Computers are so much faster now, so we could probably fit this model more quickly, or more likely we would fit a bigger model. Having a better computer frees us to do something dumber, so maybe we would. It's hard to know. We probably were. We actually were running these things overnight, but I guess it wouldn't take overnight anymore. We needed to check the models. I told you that Bayes quote from before. There are a lot of different ways of checking the models. We should check whether the inferences make sense. We check whether the posterior is consistent with the prior. We check whether the posterior is consistent with the data, and we check with new data. Each of these is possible. I don't have a unified theory of model checking. I think these are all important steps. And I would distrust someone who says you should only do one of them. So someone who says, just do this, that's silly, you should do those other things. People who aren't willing to see whether the parameter inferences make sense, that's important too. What does it mean to say something makes sense? What that really means is you're comparing it to prior information that you didn't bother putting in the model. So saying that something makes sense is really like you're throwing in more prior information in a lazy way. But that's okay. There's always some bit that you haven't thrown in. So it always makes sense to do that. Then I have the checking the fit of the data and consistency with the prior is sort of a more general issue with the model that you fit, because we know our models aren't perfect. Okay, so I believe two slides. Okay, whoops, here. If you care about pharmacokinetics, these models are complicated. Sometimes I said the complexity makes it easier to add information in other places. I don't remember what I meant by that, so I won't try to figure it out right now. One of my themes, sometimes Bayesians say, like sometimes someone's teaching a Bayesian class and they'll say, the first thing you have to do is forget everything you learned about statistics before. And I don't say that. What I say is the first thing you have to do is forget everything you learned about Bayesian statistics before. Because I think people have a bad, they talk about Bayesian statistics being subjective information. They talk about the posterior probability the model is true. All these things that make no sense. My models aren't true. I don't do Bayesian inference in order to pick the correct model or even to average over models. I try to construct reasonable models that then I try to destroy. I try to defeat and then replace by new models. So it's just like computer programs, right? Every once in a while you're in a situation where you have 3 programs and you want to pick which one to use or even average over them and sometimes use one and sometimes the other. But when you're building a computer program as opposed to using someone else's, you usually try to make it do what you want it to do and then you try to break it and then you try to improve it and then you try to break it some more and you improve it and at some point it's easier to start up and make a new one. It's sort of like science. It's like the structure of scientific revolution. It's like a lot of things that I've written a lot about that I won't talk about, but it's not the way Bayesian statistics is traditionally taught by people other than me. There is a lot of, I wrote about this too, though if you read the Wikipedia article on Bayesian inference, it says stuff that I completely disagree with, because it says that Bayesian inference is all about picking models and figuring out the posterior probabilities of models, which I don't think it is. So I want you to forget this. And what I want you to think about is that Bayesian analysis is a way of improving what you have already. It's a sort of not something different. So what are the applied pieces of Bayesian analysis? There's regularization. So regularization is what I was talking about at the very beginning. It's saying that you have a model which, for mathematical reasons, includes things that don't make physical sense, and you want to use soft constraints to get rid of those possibilities. Soft constraints are computationally nicer than hard constraints, and they also generally match our scientific understanding better. It's very rare that you really know something is positive rather than negative, but it's not so uncommon that you sort of know that something is more likely to be here than there. Accounting for uncertainty is basically that's central to the Bayesian approach, that you can take an estimate or a classifier or whatever, and you can sort of stick it into Bayes and turn it into a probabilistic classifier. Model checking. So Bayesian statistics, by being able to give predictions for anything, also gives us the ability to check a model in a way that classical models are much more hard to check. The magic word is generative. So Bayesian models are all generative. So you can check generative models by generating data and comparing them to real data. You can't easily check non-generative classifiers or estimation procedures. They might be great, but you can't easily check them. I think this is important because old-time Bayesians had a really bad attitude that they never wanted to check their models. They'd say their models are subjective, so they were uncheckable, which was stupid. We can combine information. This is happening in different ways. We have the data and the prior. We're also combining information across subjects in our study. We have 6 people, and so we do this partial pooling, as she'll appear in a moment. Better dialogue with the subject matter experts. So this is what my PhD advisor used to say all the time, was that, which I've parroted at some point, that okay, you're computer scientists, many of you. Okay, if someone comes to you and they're doing an applied problem, okay, you want them to talk to you about what they want done. You don't want them to come to you and say, I want this much register space, and I don't want a pointer-based language, and I don't really want strong typing here. What I really want is, I want a language that's a little bit sort of more like, well, a few years ago, once when I was in college, I programmed something in Fortran, and I sort of like some of that. But okay, you don't want that, right? You don't want them to tell you about compiler design. You want them to come to you and say, I want a program that translates this language into that language, or I want you to give me a program that that can solve this problem, and then you want to solve the problem, and then you want to interact with them in that way. Well, similarly with statisticians, we don't like to talk to people about statistics. Okay, so if you notice, it's like, where are the loose ends in a project? You want the loose ends. I don't want to say, okay, this happens a lot in classical statistics. Say, I have this project, this is pretty good. Where are the loose ends? Well, the loose ends are, I'm not quite sure about my confidence coverage here. I better do some simulations of that. Or, I'm not quite sure if my hypothesis test, you know, has the right shape of its rejection regions. I think there might be some instability in that, and I bet, okay, and that's not good. And what's really bad is when scientists start coming to me and start trying to talk about statistics with their silly ideas, okay? And they'll say, you know, I want something robust or whatever, or some goofy idea that they have. So actually, if you notice the loose ends in this project, they're all subject matter loose ends, except for the loose end of constructing that damn thing to, okay. So the subject matter loose ends like, how could we get more data on some of these hard to find parameters? Or what, you know, like how could we, look, there's a problem with the model because it doesn't capture the short time scales very well. Things like that. That's what you want. And so one of the things that Bayesian inference can give you is it connects the model to the data in a way, and it allows to have more scientific interactions. At least that's how I see it. And so the purpose of this talk was to give you a sense of how I would do things, and also how all these different pieces fit together. So at this point, ask any questions or give me any comments you have. Yes.
Why don't people do this anymore?
Why don't they do this toxicology?
Well, no, you said at the beginning of the talk that we should ask why this was done 15 years ago.
I think they're still doing it. No, they're definitely doing these models. And because before we came along, there were actually existing computer programs that fit hierarchical models for like 2 or 3 compartment models. And people would try to tweak them to fit 12 compartment models. And they'd be like, you know, like when you have a program, like they would sort of try to trick it into fitting more complicated models. So why aren't they running this? I'm not sure. I don't really know the toxicology world. I think toxicology is sort of a funny thing because it's like there's no one really paying for it except like governmental agencies, and that's sort of a mess. Their motivations are complicated. Pharmacology, though, like drug companies are very interested in this. And I did talk about this. I went to Novartis in Switzerland and talked about this, and they said that they tend to fit simpler models, and they said they just have a lot of constraints. They just don't have the time to fit a more complicated model. So I don't really understand why it's not all done more, actually. I mean, I guess my guess is that people, maybe correctly, people put more effort into the biology. And so what they'd really like to do is figure out exactly what's happening inside the liver rather than trying to squeeze the maximum amount of information out of this bit of external data. This is very indirect data. So I think the probably the best long-term scientific approach is not to get these kind of external indirect data and squeeze information out of it. It's probably better to go, send a microprobe into somebody's liver and see what's going on. So this kind of statistical approach might be always the best way to analyze whatever data you have, but it might be that it's always a better idea to just get better data, not to waste your time on the statistics. But I'm not sure. There is a sort of industry of people doing this. It's just people who you don't know, but there's a whole world of these people. Yes?
I'm not sure this is the story you're telling today, but you mentioned how you want to use Bayesian inference to evaluate your model, break it, and keep refining it. Did you have that story here? Did they come and handing you the 4-component model and say, work with this?
Did we break this? No, we refined it, but we never really broke it. Yeah, I mean, we added pieces to it. We added parameters and complexified it, but we didn't break it. I mean, what would be an example of a model that, I think probably, it's hard to say because I think the kind of models that you all fit, it's not like anyone ever broke it. Like it's just that it kept getting elaborated on in different directions. That's a funny thing because I am always talking about how I break the model and refit it, but like when does it always occur? I'll have to think about that one. Maybe I never actually do that. Maybe it's just all talk. I don't know. You can't end with that one. That makes, okay.
So one thing that's happened since 1995 is you've done a lot of work on social science, and especially political science. And so I'm wondering if you were to take 6 young developed countries, could you predict could you use that to predict in America how long it will take for the bile and the other toxins to leach out of the body politic?
Well, okay. So in political science, actually, a lot of people do comparative analysis, and there is a little bit of, people are doing more hierarchical models. So one of the challenges in political science, you have data, if you have data on 20 different countries and you want it, so people will do a 2-stage model. So in each of the 20 countries, they'll run a little regression of some sort, and then they'll analyze the regression coefficients in a second stage. And it seems like it would be better to do a hierarchical model. One of the challenges is that you'll often get different data in the different countries. So this is actually pretty clean because the 6 people, the same things are measured in the 6 people. So if you have data on 20 different countries and you have different measures, it's a challenge. So I've talked to people about that. It can be difficult. I mean, I think it's sort of the right way to go. But.
I think maybe where I was kind of trying to go with this last point right here, which I find really interesting. Like, what do you find are the best tools and such you can develop in order to help people on the science end of things use your models maybe more flexibly to learn? And I get maybe not great, but we're learning the models like you said in this experiment. You could say you should put mixing into this. Are there approaches to help people on the science end get these tools and say I should put mixing into this more by themselves, or how do you manage that dialogue?
Okay, let me give you a simpler example. Logistic regression, or linear regression for that matter. Regression models for prediction. So one of the nice things you can do. So suppose I have a hierarchical structure. So I'm predicting some outcome, and people are in groups. So I could have individual level predictors and group level predictors, individual level error and group level errors. One great thing about hierarchical models is that I can keep adding predictors at both levels. Now, in a non-hierarchical context, a hierarchical model is sort of a Bayesian idea because it has multiple variance components. In a non-hierarchical context, like once you've included indicators for groups, you can't really include group level predictors. And conversely, if you have group level predictors, you can't really put in indicators for groups. You can do one or the other. And then people will have an argument about whether they should be putting in individual level predictors or group level predictors, and whether they should use clustered standard errors and different things like that. If you get a discussion about, if you're in the hierarchical model, then you can talk about the group level predictors you're putting in, while also including group level variation. Now that obviously it doesn't eliminate the need for statistical discussions, because you still have, if you put in a bunch of group level predictors using least squares, eventually you have issues of instability and estimation, and you want to put in more prior information on them. But this is the idea of what I'm talking about, that you'd add information into the model, and the discussion would sort of be able to go that way. So then maybe the statistical question might be, how can you add more information, rather than how many pieces of information are you allowed to add. And there's a lot of sort of old-fashioned statistics where people tell you can't do stuff, right? And there'd be like, where the message would be that that it's bad to have more information. That when you have more information, you have to do a multiple comparisons correction or whatever. And I don't like that sort of thing. Yes?
When you saw information on the Wikipedia page on Bayesian statistics that you didn't like, did you consider editing the page?
Well, I thought about it, although, actually, I keep quoting that as saying I don't agree. So if I edited the page, then I'd have to say, I don't agree the old page. I guess I think we have one more article that's like in review. Maybe I'll edit the page. I could do that and see what happens.
Service for everyone who wanders there for whatever reason.
No, I understand. I mean, what I would do is I don't think I would just delete it all. I would just say I would say not everyone agrees with this. That certain renowned statisticians or whatever don't feel differently, and here's something like that. So yeah, a little puffery maybe, whatever. I guess I should do that. That's it? You're ending with a Wikipedia comment? That's the best you all can do? Thanks.
So you've got 6 people forming this hierarchical prior set. And how comfortable are you with the distributional assumption that you've given for the relationships of these 6 people, since you have 6 people forming that set?
How comfortable am I with the distributional assumption? Well, I like the way you put it, because sometimes people would say, do you really think those 6 people are exchangeable? And I would never say that, because exchangeability is just a description of the mathematical model you're using. But sure, I guess they're not really Gaussianly distributed. I don't know what much more you could do with 6 people. I mean, they're not very well they're not that well distinguished otherwise from each other. I mean, we don't really have. The experiment was designed, for better or worse, to use people who are pretty similar. So what information we have to distinguish them are their weight and their adiposity and stuff like that, and that's actually already included in the model. So it seemed reasonable. We didn't think too much about it. In the example of the 20 countries that we talked about, then it's more of a challenge that you'd want to put in group-level predictors and try to explain some of the differences that way. And one of the things, actually, I didn't really talk about, but I'll show you a picture. One of the things that sometimes comes up in hierarchical models is that uncertainty and variation are roughly the same. So do you see this? It's not a coincidence. So if you see this, those of you at home can't see it, because unless that camera is moving and tracking me, I'm hiding, actually. Person A differs a little from person E. They differ just a little bit, right? Like, they differ by about as much as there is uncertainty. This is typical, that the variation and the uncertainty, the posterior variation and posterior uncertainty are comparable. And now, why would that be? Now, the reason why is that you start out in a world with a lot of variation, but then you try to explain that variation. Well, in this case, much of it was done before the experiment started by taking 6 very similar people. Suppose the variation were much larger than the uncertainty. So we knew person E was like here, and we knew person D was here. If that were true, we'd really try to understand what's so different about person D and person E. We might put that into the model as predictors, and then the residual variation would be comparable to the uncertainty. Now, what about the other way? Is it possible? So I said, is it possible for the variation to be huge compared to the uncertainty? And the answer is, if that happens, you'd want to explain the variation until it reached this picture. What about the other way? Could the uncertainty be huge compared to the variation? Well, not really, because if the uncertainty were huge, you wouldn't have all, if these had like huge uncertainties, they wouldn't all overlap with each other, because you just wouldn't have enough information to locate them that well. I'm not saying this well. I'm sorry, this last bit. So I'll have to think about a better way of phrasing it. But I do feel that that the result of a lot of hierarchical models is that your uncertainty and your variation are comparable, just related to everything else. So at this point, there's one more question, then we'll stop.
It's a vague question. I'm not able to articulate it well. That's why I was holding back all this time. Like, Bayesian inference, Bayesian statistics makes sense to me, and it's very sort of compelling when you have some subject matter expertise and some data, and you want to combine them and so on. But every now and then, problems where there is a lot of data, but there either isn't any subject matter expertise because we really don't know how these things relate, or we don't have access to subject matter experts. So you just have certain observations, and based on that, you want to build some predictor, and you believe there are some latent variables, some latent parameters, and you'd like to do that. And in that setting, what would you advise? I mean, because I'm thinking now that I can make predictions with my model, okay, but what's the notion of model checking now, and what do I do there?
So, I mean, a lot of work I've done has been in problems where very little subject matter expertise is used. So, yeah, if I've no subject matter expertise available, then I'll use much weaker prior information. And you can do that. It wouldn't work here. So in this example, it would fail, but a lot of the political science examples I've had, there's a fair amount of data. You use your data, and you can't learn quite as much that way, but sure. I still believe in using a bit of prior information, because even when I don't have subject matter expertise, I usually have certain constraints. Like I usually, if I have parameters, if I have problems scaled so that numbers are typically in the order of magnitude of 1, then I'm usually not going to have coefficients of 10 or 100. So it can work to regularize away extreme cases like that, can make things more stable. And I talked about mixture models already as another example. So I do think that the Bayesian approach of using prior information can help, but then you just have a lot less prior information. And that's, in some way, this is a typical example for me.